Hey everybody, it's Friday, March 5th, and as you can see here in the aim today, our goal for today's video is going to be all about how we can relate linear quantities of motion to their rotational counterparts. Now, like I said, we are going to spend the vast majority of today's video talking about what is shown here in the aim, but the first thing I want to do before we get into that is review the problem that was assigned to you at the end of yesterday's video. So at the end of yesterday's video, I showed this problem to you and I asked you to solve it and submit it. This problem is in the rotational motion packet on page 3, number 20. It says here a cooling fan is turned off when it is running at 850 revolutions per minute. It turns 1,250 revolutions before it comes to a stop. What is the fan's angular acceleration, assumed to be constant? And then B says how long did it take the fan to come to a complete stop? Now, as I mentioned yesterday, these textbook problems are annoying because they are going to always give you units which you are not going to use because you need to use all these values in units of radians and seconds instead of revolutions and minutes. You don't actually have to show the work for the conversions, but while we're going over the thing, I'm just going to show it here. The first thing we have to convert is this speed here, 850 revolutions per minute. And to convert revolutions per minute to radians per second, you multiply by 2 pi over 60. We put 1 revolution in the denominator and 2 pi radians in the numerator, and then 1 minute in the numerator, 60 seconds in the denominator. Minutes, cancel minutes. Revolutions, cancels revolutions, and we're left over with radians and seconds. When we take 850 and we multiply it by 2 pi over 60, we get 89.011 radians per second, or to 2 sig figs, as the original measurement is given in, 89 radians per second. The problem also gives us this angular displacement here of 1250 revolutions, and to convert revolutions to radians, all we need to do is multiply by 2 pi radians over 1 revolution. Of course, there the revolutions cancel. And so when we take 1250 and we multiply it by 2 pi, we get 7853.98 radians, which to 3 significant figures, like is given in the original measurement, we get 7850 radians. And with those calculations, now we're ready to make our list of knowns. So it says the cooling fan is turned off when it's already running at 850 revolutions per minute. So that means our initial angular velocity here is 850 revolutions per minute, or as we just calculated in radians per second, 89 radians per second. They tell us here that the angular displacement was 1250 revolutions, which, as we just calculated, is equal to 7850 radians. Now, notice here, if we go back to the text of the problem, it tells us the cooling fan turns that many revolutions before it comes to a stop. And so that means our final angular velocity here is 0 radians per second. And we are looking here, at least in part A, for the fan's angular acceleration, which is given the symbol alpha. So looking at the knowns and the unknown here for part A, the variable that is conspicuously missing is the time. And so it should be pretty clear to everybody, like it was for kinematics when we were doing this for linear motion, when you're not given the time and you're not asked for the time, a perfectly good equation to use is the time-independent equation. Omega final squared equals omega initial squared plus 2 alpha delta theta. Now, because the final angular velocity here is 0, we end up solving this thing for alpha and getting negative omega naught squared over 2 delta theta. Notice we subtract the omega naught squared and then divide by 2 delta theta. And so when we plug our numbers in here, we get negative the omega naught, which is 89 radians per second. And we divide that by twice the angular displacement, which is 7850 radians. And when you do that math here, 89 squared, sorry, I forgot to put the square on the outside of that initial velocity, 89 squared and then divided by 2 times 7850, you end up getting an angular acceleration of 0.5045 radians per second squared, which to 2 significant figures, because the omega naught is given to two significant figures, comes out to 0.50 radians per second squared. And of course, notice here, that should be negative from the negative sign out there in front of the omega naught. So we have a negative angular acceleration, and that should make sense that it should be negative because, well, in order to slow down an object in linear motion, you need an acceleration that acts opposite the direction of its linear velocity. And it works the same way here too. If we want an object's angular velocity to decrease, we need an angular acceleration that acts in the opposite direction. And so our angular acceleration here is negative 0.50 radians per second squared. For part B, we're looking for the time. And there are a number of equations that you can use for this, but I think the most straightforward equation that you can use for this is just the final angular velocity equation, omega final equals omega initial plus alpha t. If we solve that for the time, we get omega final minus omega initial over the alpha. Our omega final here is 0, so we just get negative omega naught over alpha, and so that gives you negative 89 radians per second over our alpha here, which we found was negative 0.50 radians per second squared. And so notice here, this is going to work out to be positive, and that gives us a time of 178 seconds, which to two significant figures, of course, we can round to 180 seconds. And that's what the work should look like for that problem at the end of yesterday's video. Let me know if you have any questions about that. The techniques that we are applying to these problems are fairly familiar, or at least should be fairly familiar, because you've been doing these like kinematics problems for a while now. I think it really just takes a little bit to get comfortable with. But like, if I gave you a problem that said an object started with an initial velocity of 89 meters per second and its displacement was 7850 meters and it stops, so has a final velocity of 0, what's the acceleration and the time? Nobody would second guess that. You'd be able to answer that in less than 5 minutes. And so here, hopefully you realize the only difference really is just the symbols. And once you get comfortable with those symbols, then you shouldn't have to think too hard about these. Okay. And that brings us to what we were talking about at the very start of this video, which is the aim for today. How can we relate linear quantities of motion to their rotational counterparts? What I told you when we first started in this topic was the most important thing in rotational motion is recognizing that every rotational quantity has a linear version and vice versa. And so what we want to do today is talk about not only just what is the linear quantity that is related to the rotational quantity, as we have been doing, as we've been going through all of these different quantities, but we want to talk about how, given the rotational quantity, we can then go back and calculate the linear version of it. For example, if we have the angular velocity, how could we calculate the linear velocity of a point on that rotating object? Or if we have the angular acceleration, how could we calculate the linear acceleration of a point on that rotating object? And I think the most important thing for you to understand and recognize about what we're saying here is that the linear acceleration of the rotating object is going to be 0. The object is not going to be moving in space. It is just going to be rotating. But to conceptualize this and to discuss it in detail, we are always going to talk about a point on the rotating object. And so literally, if you just imagine like a disk spinning in front of you, if you just drew a point on that disk, that's what we're talking about, the linear velocity and linear acceleration of that point. And so the big question here to start us off is going to be, for a point on a rotating disk, if we know the disk's angular velocity, how can we determine the linear velocity? This is an important exercise to think about. Number one, because this is just important for rotational motion in general, but number two, because it's something that you've already done. And so to get this point across here, I want to show you a simulator, because I think the simulator does a pretty good job at showing you the relationships. And so strangely enough, what you'll notice when they ask these questions about a point on the rotating object. They use a ladybug on a disk all the time. I don't really get it, but anyway, this is what they use. And so the point we want to make here is that when the disk has zero angular velocity, there is no tangential velocity, or there is no linear velocity. But when we increase the angular velocity and just make it some value, because the object is moving in a circular path now, it has a tangential velocity. Remember, I said a lot of this stuff is related to uniform circular motion. And so here, you notice the simulator is going super, super slow. The ladybug moving around in the circle has a tangential velocity. I want you to pay very close attention to the length of that velocity vector. What happens to the length of that velocity vector when I increase the angular velocity? That's the first question. And I think what happened is pretty obvious. When we increase the angular velocity, what we see is that the linear velocity, or the tangential velocity, increases. But now we also have a good question to ask, because we can clearly see that linear or tangential velocity is related to the angular velocity. But what is the effect of the radius? That's another perfectly reasonable question. And so we'll actually pause this thing once again to just make them in the exact same line here like this. It's not cooperating. This thing is running very slowly. I would post this for you, but it's really working so terribly because it's using like a Java simulator of the simulator, because this is an old Java simulation. But hopefully you can tell how the velocity vector for the ladybug compares to the velocity vector of the beetle. Maybe it's a beetle, not exactly sure. Clearly, the radius is going to have some effect on the tangential velocity as well. And that should make sense too. What we see is that the linear velocity increases when the radius increases. So there are two key observations that you need to have taken away from this simulator. Number one is the linear or tangential velocity increases when the angular velocity increases, and the linear or tangential velocity increases when the radius increases. That should make sense if you really think about it. And I'd like you to write this under the heading angular velocity to linear velocity. What we saw is that as the angular velocity increases when the radius is kept the same, that was just what we did with the ladybug, the linear velocity of the object increases. Why does that make sense? Well, if the radius is kept constant, the object is moving around in a circular path, and it's doing that faster. It's moving the same amount of distance, but it's doing it in less time. And so let's actually go ahead and just write there, same distance, less time. That should make sense why the velocity is larger. Same distance, less time. What we also saw is that as the radius increases when the angular velocity is kept the same, the linear velocity of the object increases as well. And I think the reason why is very straightforward. The object is moving in a circular path of a larger circumference if the radius is bigger. And the object moving in a circular path of a larger circumference has to move faster in order to travel a larger distance in the same amount of time. They are on the same rotating object. In that simulator, if this is the center of the circle, the ladybug was traveling in a smaller circle, and the beetle was traveling in a larger circle. And because they were on an object that the whole thing was a fixed rotating object, they were rotating together, meaning it took them the same amount of time to go around the circle once. But because the radius of the circle influences the size of the circumference, the object with a farther distance from the center of the circle is traveling more distance in the same amount of time. And that's ultimately why we can conclude that its speed has to be larger. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, so let's write down a big important note here for the beginning. The linear velocity of a point on a rotating object, based on what we just said, is directly proportional to the radius of the circular path that point is traveling on. And it's directly proportional to the angular velocity of the rotating object. Take a second to pause this video here and write that down. And when you hit play, we'll move on. And so because the linear velocity is directly proportional to the radius and directly proportional to the angular velocity, it should not be a surprise what the equation looks like. The equation is V equals R omega, where V is the tangential velocity of the point, R is the radius of the circular path traveled by the point, and omega is the angular velocity of the rotating object. Notice here, in a way that should make sense, we get units of meters per second for our tangential velocity. The reason why we get meters per second, though, is a bit confusing. So I'd like you all to write this down first, and then we'll get into the reason why the units just work out to be meters per second. Now, usually a pretty common question that I get when we bring this point up is if we are getting the linear velocity v by multiplying r and omega, and r is measured in meters, and omega is measured in radians per second, then why don't we get meter radians per second? And the answer is a little weird, but it's that the radian is not a real unit the way other units are real units. It's basically just a placeholder. And what that means is that when you combine any unit that contains radians, you should be treating the radian as a 1. The reason why is pretty simple. If you remember the other day, we said the equation 2 pi equals circumference over radius, which describes a whole circle, can be used to describe only a certain arc section of a certain circle, where S is usually the symbol we use for the arc length, R is the symbol for the radius, and of course theta is the symbol for the angle. And if we write an equation for the angle in just the way that the angle, which represents 2 pi here, is equal to the circumference, which is the length of the full arc, or the circumference, we get divided by the radius, we get an equation here that says theta is equal to the arc length over the radius. And notice when we solve this for the angle, we get meters divided by meters, and the units cancel. Radians, then, really just kind of functions as a placeholder. It is certainly a bit more complicated than this. But what you need to know for this course right now at this very moment is that when you combine any unit containing radians with any other unit, the radian part should just be treated as a 1. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Let's go ahead and take a look at a problem. This problem here is from the Gravity and Uniform Circular Motion packet, and it says here the diameters of the main rotor and tail rotor of a single-engine helicopter are 7.60 meters and 1.02 meters, respectively. The respective rotational speeds are 450 revolutions per minute and 4,138 revolutions per minute. The question says to calculate the speeds of the tips of both rotors. So notice here, they told us the diameters, and that's the first annoying thing about this problem. What else is particularly annoying about this problem is they've given us these rotational speeds in revolutions per minute. You can just go and Google these RPMs to radians per second and find a good calculator. I'm not going to show this calculation again because I've shown them a bunch of times. You should have some sense of how to do this already. And so we're just going to get right into it. We'll start here with the main rotor. I'm going to change this ink back to black here. So for the main rotor, they told us the diameter was 7.60 meters. And so that means the radius is going to be 3.80 meters. And they told us that the angular velocity of this rotor, as you can see there, is 450 revolutions per minute. Remember, you multiply that by 2 pi over 60. And when you do that, rounding the number to two significant figures, you get 47.1 something. And so we'll call that 47 radians per second. And we are looking for the velocity of the tip. And that's why we're using the radius, or the full radius, I should say, because the tip of the rotor, or the tip of the propeller, whatever you want to call it, is at the very end of that radial distance. So according to the equation we just derived here, we get V equals R omega. And so we have R, 3.80 meters, times 47 radians per second. And when you do that math here, 3.8 times 47 is 178.6 meters per second, which is approximately equal to 180 meters per second. Remember, you treat the radian as a 1, so you basically just ignore it. We have meters times 1 over second, or meters per second. For the secondary rotor, we engage in exactly the same process here. This description in the beginning told us the diameter of that rotor is 1.02 meters. And so that means the radius is going to be 0.510 meters. They told us here that the angular velocity of this secondary rotor is 4,138 revolutions per minute, which to four significant figures, once we convert it, is going to give us 433.3 radians per second, and we're looking for V. So we use the same equation, V equals R omega, and we have V then equals 0.510 meters times 433.3 radians per second. And so that gives us a tangential velocity of 220.983 meters per second, or to three significant figures, 221 meters per second. And that's it. Now, of course, the first time that I was teaching this, because my degree is just in physics, and I don't know a lot of things that you know, there were kids in the class who freaked out when I said the following. I said, and if you look at the end of the problem there, it says to compare these speeds with the speed of sound. You could just take those speeds and divide them by the speed of sound, and it'll give you a number. Why exactly they're asking you to do that, I haven't the slightest idea. But, whatever. They're just asking you to do that as an exercise, I guess. And the kids freaked out because they said, yo, mister, you don't know that? Apparently, as I've learned from my students over the years, Bernoulli's principle breaks down when the tip of the rotor approaches the speed of sound, as hopefully you learned in CHOP, or at least some of you learned in CHOP, depending on your course of study in CHOP. And so they want you to compare these tip speeds to see if they are close to the speed of sound, to see if they are still generating enough lift as they should be. And so we could do that simply by taking the speed and dividing it by the speed of sound. And so if we take 180 meters per second over 343 meters per second, we get 0.525. This is only 50% of the speed of sound, still not that close, should be good enough to operate as intended. And then, of course, for this secondary rotor, we have 221 meters per second over 343 meters per second. And what we get there is 0.644, 64.4% of the speed of sound, still well within the range. And that's it. Take a second to pause this video here and write that down, making sure you have all parts of the solution in your notes. And when you hit play, we'll move on. All right, now before we move on, now that we've done one of these, I think it would be important to comment on one point in particular. And that is that in general, to convert a rotational measurement to its linear counterpart, you'll multiply the rotational value by R. This, you'll notice, is going to come up again and again and again. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, this next point here is a little confusing, but it is worthwhile for us to discuss because I think you know enough at this point to be able to understand it. But I still want to just make sure we can flesh it out here so that it is easily understood by all. When a rotating object has an angular acceleration, meaning the angular velocity is changing, if we're looking at a point on that rotating object, it actually has two accelerations. One of them is called the tangential acceleration, the other is called the radial acceleration. The tangential acceleration, the acceleration tangent to the circle, occurs because the angular velocity of the object is increasing. And so that means it's going to have a velocity tangent to the circle, and that velocity is going to be changing. And so it will have a tangential acceleration as well. The point, though, also has a radial acceleration. In other words, a centripetal acceleration, because the point is moving in a circular path. And so because it's moving in a circular path, there must be some acceleration directed towards the center of the circle. As a result, when we talk about these linear to rotational transformations, we have to talk about both kinds of acceleration. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So first up, we'll start with the radial acceleration, since you've already seen centripetal acceleration in this course before. When an object is rotating, a point on that object experiences a radial acceleration, or an acceleration which points along the radius toward the center of the circle. This is basically the centripetal acceleration. And so it shouldn't be a surprise what the form of this equation is, because it's really all based on the centripetal acceleration equation, v squared over r. So what we need to do here in order to get this into the form we want is basically rotationalize it, if you will. And the way we do that is as follows. We start with the equation v squared over r, and we acknowledge that we just derived an equation that says v is equal to r omega. So we plug in r omega for our v. Of course, because the v is squared, we have to square it. And when we square r omega, we get r squared omega squared. And what you should realize in a pretty easy way is that the r down there cancels one of the r's up here. So we get a radial equals r omega squared, where r is the radius of the circular path traveled by the point, omega is the angular velocity of the rotating object, v is the tangential velocity of the point, and the a rad, as we've labeled it here, is the radial acceleration. And of course, the units there are meters per second squared. That should make sense here because the radius is measured in units of meters, and omega, once we square it, is going to give us units of radians squared per second squared. But of course, because we always treat the radian as a 1, whenever we incorporate it, we just get meters per second squared. Take a second to pause this video here and write that down. And when you hit play, we'll move on. That brings us to tangential acceleration. As we mentioned here, when a rotating object has an angular acceleration, a point on the rotating object itself is experiencing a change in its tangential velocity, and thus is experiencing a tangential acceleration. And as we mentioned before, the general theme of converting angular quantities to linear quantities is taking that angular quantity and multiplying it by r. So the tangential acceleration equation is r alpha, where r is the radius of the circular path traveled by a point on the rotating object. Alpha is the angular acceleration measured in radians per second squared. And the tangential acceleration is measured in units of meters per second squared. Now, as we mentioned here, the reason why you get meters per second squared is because you treat the radian as a 1. Meters times 1 over second squared is meters per second squared. So that's the unit for the tangential acceleration. Take a second to pause this video here and write that down. When you hit play, we'll move on. This problem here is in the rotational motion packet. It's page 3, number 10. It says a rotating merry-go-round makes one complete revolution in 4.0 seconds. What is the linear speed of a child seated 1.2 meters from the center? And then it says, what is her acceleration? Give components. We'll start with part A first. It says here the merry-go-round makes one complete revolution. And so that means the angular displacement here is going to be 2 pi radians. And it says it does that in a time of 4.0 seconds. We are looking for omega, v, and then any accelerations, which we'll do later on. So the first thing we need to do is find omega. And omega is going to be delta theta over t. There is no information here given to suggest that the thing is accelerating. And so omega equals delta theta over t. And so we have 2 pi radians over 4.0 seconds. And that gives us an angular velocity of 1.57-ish radians per second. And so to 2 sig figs, because the 4.0 is given to 2 sig figs, we'll call that 1.6 radians per second. Now, of course, we were asked to find the linear velocity of a child moving at 1.6 radians per second, seated 1.20 meters from the center. That means the radius is 1.20 meters. So we're looking for v. V is equal to r omega. And so that means v is our radius, 1.20 meters, times our angular velocity, 1.6 radians per second. And that gives us a linear velocity of about 1.92 meters per second. Now, for part B, notice it says here, give components of the acceleration. Something that's important to realize is we refer to these as components of the acceleration because if the radial acceleration is pointing towards the center of the circle and the tangential acceleration would be pointing tangent to the circle, those are at right angles like any other two vector components are. Now, something that should be noted here is that since there is no information in the problem given to indicate that the angular velocity is changing, we can say here that A tangential equals 0 meters per second squared. And so the only thing we are looking for is the radial acceleration. We know here that the angular velocity is 1.6 radians per second. We know that the radius here is 1.20 meters. And that means to look for the radial acceleration, we need to use the equation we just developed, which is A radial equals R omega squared. And so A radial is R omega squared. That means the radial acceleration here is 1.20 meters times 1.6 radians per second squared. And when you do that math, you get a value of 3.07 meters per second squared. Again, the radial acceleration is basically centripetal acceleration, which the point on this rotating object, or the kid sitting in the seat, definitely has because they're moving in a circular path. Because there is no information given in this problem to suggest the angular velocity is changing, we say the tangential acceleration is 0. And with that, we are done with kinematics for rotational motion. You could write this down if you'd like, but I think that this chart is pretty cool because it summarizes basically everything we said so far. Every linear variable has a rotational counterpart, and there are relationships between them, as shown here. And so going down the line, we have our position, our velocity, our acceleration, our kinematic equations, and notice here, that brings us to force, which is where we will pick it up next week. And with that, that is it for today and for the week. Enjoy the weekend, everybody.